Excellent. Good afternoon, everyone. Thanks for joining us today for the third seminar for spring of 2022 in the core seminar series. As you notice, hopefully we're recording today, so please be mindful and mute your microphone or pause your camera if you're not actively engaged in the conversation. My name is Andrew Bernard. I'm the Director of Centralized Core Facilities here at UMass Amherst. These seminars are intended to provide awareness to the great work being done in our cores and to give you a chance to interact with the core staff and also to talk with your peers who are actively using the cores. Today, Haochen and Zili will be discussing some of the Raman IR and XFR spectroscopy capabilities in the core facility. And as I mentioned, the seminar is being recorded so that those who aren't able to join us today can have a chance to watch later. We keep this in all past core seminars in addition to a list of those that are upcoming online. And after we get started, I'll make sure to put a link in the chat box there. I'll be here monitoring the chat for any questions you may have, but we'll let the presentation go and have some time for Q&A at the end. Feel free to put them in the chat, and if you have any questions about the facility or facilities in general, we'll be happy to answer them. So with that, I'll turn it over to the Raman core team. Thank you.
All right, thank you, Andrew. So I'll be starting from now. So basically, me and Zili, we're using the same account. So we're going to do in turns to introduce our core facilities. So in this first section, we'll be introducing basically what we do, what instrument we have, and later Zili is going to share some of the collaborations we have with industries and some of the applications we made measuring different samples. So in general, we are an advanced analytical lab in the food science department of UMass, and we mainly focused on advanced spectroscopy analysis for organic and inorganic samples. This would include agricultural sample, environmental, as well as food samples. Most of these samples are organic compounds, but we also measure a lot of the inorganic compounds, such as metals, polymers, and biomedical materials. So basically, the three major equipments in our lab are Raman Spectroscopy, IR spectroscopy, and X-ray fluorescence spectroscopy. So in these future slides, I'll be one by one introducing what they are and what they're capable of doing. So the most used equipment in our core facilities are these two DXR Raman microscope. These two instruments are benchtop models that are very powerful to deliver any chemical analysis. For example, both of these instruments can do mapping, Raman mapping down to 1 micrometer resolution, and both of these instruments are equipped with dual wavelength laser, including the 780 and 633 wavelengths. And these instruments are very smart. The measurement is all automatic. You just need to click the sample spot you're interested in, and all these equipment will be automatically measure your interested spots. So besides these benchtop models, we also equipped with two portable Raman devices. As you can see, that Raman can be made into a very small form factor. It can be packed in a suitcase and also be made into this carryable form. So all of these instruments is also able to do the similar job compared to those benchtops. But if you're interested in, for example, on-site measurement or measurement at out of the lab setting, these instruments can achieve that goal. Next, so with the IR spectrometer. So IR technique is a complementary technique to Raman spectroscopy. So both of these techniques can provide you chemical information based on the vibration modes in the moleculars. So as you can see here, we equipped with two instruments, that is the FTR spectrometer and the FTR microscope. Both of them are equipped with the ATR objective that can collect the useful IR signals. So moving on to the XRF. XRF is a technique that can help you measure the elemental composition as well as the quantification of different elements in your sample. We have two instruments that is right now registered on our website, that is Epsilon 1 and Epsilon 4. So both of these instruments is capable of measuring elements that is down to ppm level. On the left-hand side, we have the Epsilon 1 This is a small portable device that you can carry to on-site, local on-site detections. For example, you can carry this to farms, to factories for your data analysis. On the other hand, the Epsilon 4 is more sophisticated with helium flush sensor. In this case, we can detect the lighter elements such as sodium, aluminum, etc. And also the Epsilon 4 is equipped with the multi-sampler. In other words, you can prepare your sample in advance and it will measure them in a sequence. All right. And we have two new equipment that's coming soon. As you can see here on my back, this is the X-ray fluorescence spectroscopy microscope, which we just installed in our facilities. And also we have this handheld Raman right here. So both of these instruments are just recently installed in our facilities. We haven't uploaded on our website yet, but if you're interested in measuring samples using these, we're also open to your request. So basically, these slides, the first section is a brief introduction of what we are and what we do and what instrument we have. So as you can see here, we offer many services, including industry collaborations, consultations, and most importantly, we also provide surveys and advanced analysis if we have any samples available. During the past few years, we also had a lot of good collaboration between industries and small companies to help them measure a variety of samples, including polymers and some 3D printing materials, etc., etc. So without further ado, let me bring Zili back and he will briefly introduce some of the applications we did using Raman spectroscopy. Okay, Zili.
Thank you for the introduction, Andy. And good afternoon. This is Zili. So in my presentation, I will briefly talk about the Raman spectroscopy and its application on chemical analysis. So Raman is a non-destructive chemical analysis technique which provide detailed information about the chemical structure, phase, and the molecular interaction. And it is based on the interaction with laser light with the chemical bond within the sample you are going to analyze. So as you can see from here, this is the sample we're going to analyze. When the sample is scattering the laser light, there is a small amount of light that scattered at different wavelengths. And this is called Raman scatter. So Raman scatter have a lot of useful information, and this information is based on the chemical structure of the sample. As you can see of this spectrum, this is how generally Raman spectrum look like. So briefly speak, different chemicals will have its own Raman fingerprint. So by identifying this fingerprint or the spectrum, we will be able to identify different chemicals or quantify them, even they are very closely related. And in this slide, I'm going to talk about industry collaborated project. And in this project, we successfully identified two isomers. And as you can see on the right side of my screen, we have two chemicals. One is lutein, another one is zeaxanthin. So as you can see, they are isomers, which means they have exact same chemical composition, but only differs at some 3D structures. So in this project, we have successfully distinguished them, and we have successfully quantified in the mixture form. And we also successfully identified the chemical change after the heat treatment. Moreover, we successfully identified the chemical distribution in the emulsion structure. So in this experiment, since these two compounds are lipophilic compounds, we dissolved them into the oil in 1%, individually and in the mixture. As you can see here, is the background of the oil control. And when we made a sample dissolved in the oil, we found that these two compounds could be successfully identified through the oil solution. As you can see, these peaks are the signature peak of these two compounds individually and in the combination. And when we enlarged this spectrum, we found that the xanthine has more sensitivity to Raman measurement, as in this demonstrated by 1% of this compound had significantly higher Raman intensity. When we enlarge this spectrum, we found that even though these two chemicals are highly similar, but we still found that they have different peaks at different wavelengths. For example, the xanthine had a peak at 1590, and the lutein had 1595. So by identifying these peaks, we will be able to identify in the mixture form. And after calculation, we found that theoretically we have 83% of lutein and 17% of the xanthine, and this is corresponding to the actual amount. As you can see, we have co-efficiency of 0.9974, and this is a very powerful method that we can identify different structure even in the isoform. So besides that, we also found after the heat treatment, lutein showed a slightly shift or a new peak at this position. And when we enlarge this peak, we found that this is a significant change. And in this way, we are able to identify the stability of your compound after different treatment. For example, like heat or microwave or sonication or long time shelf life. And we will be able to identify those small changes. And since lutein is a bioactive compound, but it's lipophilic, it has low water solubility or bioaccessibility. So we encapsulate it into the oil in water emulsion, and we want to measure if the emulsion excess is a success, which means we want to measure if in this droplet, a lutein is successfully encapsulated into it. As you can see from this image, the blank dot represent an oil droplet. We want to know if inside of this oil droplet, we have lutein in it. So we did a mapping. As you can see, we scan this rectangle area, and we found that this peak is the signature peak of oil. And we can see in this heat map, the oil is evenly distributed. So the majority of the area is showing green and blue, which means they have not conjugated. It's a demonstration of the success of oil droplet. And later on, we try to identify if the lutein is successfully encapsulated into this oil droplet. And we select this signature peak, which is a peak represent lutein. And we found that at this position, which roughly is in the center of this oil droplet, we had a red dot right here, which indicate the higher amount of lutein is in the middle of this droplet. And with this information, we conclude that this nano emulsion successfully encapsulate the lutein into the oil droplet and to improve its water solubility. And in this slide, Andy will talk about the third enhanced Raman spectroscopy. Andy.
Thank you, Zili. So it's my turn again. As you may as you may know from Zili's previous slides, some of the materials or compounds are not that Raman active. To some cases, if you have a very low level of analyte, sometimes it doesn't generate enough Raman scattering to be detected by the instrument. So in this case, a new term, we will introduce a new technology called surface enhanced Raman spectroscopy. In this case, as we can see, we have a little bit different than the previous technique. We introduce a layer of metallic nanostructure here. So the principle is the same. You will have Raman scattering generated when your compound is shot by the laser light. But here, when your compound is very close to the metallic nanostructure, these nanostructure will create what we call the hotspot. So this hotspot will greatly amplify the Raman signal, making these techniques more sensitive. Sometimes we can detect your analyte down to ppb level. So since we introduce the nanostructures, there's more application to be made. For example, the search substrate can be made into different form factors. Some substrate have aptamers on it. Some substrate can detect headspace. So the shape or form of these search substrates greatly enhanced its the application for Raman spectroscopy. I will share some of these search substrates in these slides. As you can see here, there are many commercial search substrate available on the market. Most of them are solution-based or substrate-based. The solution-based is basically the nanoparticles colloid solution itself. Usually what we do is we mix this colloid solution with your target analyte solutions, and by incubate them together, you will have an enhanced Raman signal. The other search substrate is solid-based. As you can see here, we have a lot of these substrates available, but if you see, most of them are chipped-like substrate. Your samples are mostly, you have to prepare your sample into solutions and drop on these substrate, or these substrate needs to be incubated with your samples to have useful signal. So during the past few years, our lab has developed many innovative search substrate that is easy to make, low cost. And as you can see here in this picture down, we have many shapes and forms. All of these are search substrates. So these substrates greatly expand the applications of a search or Raman spectroscopy, and these substrate overcomes multiple restraints of the solid substrate. And let me briefly talk about these substrates. Here on the very left, we have the silver dendrite. Here we have the search filter membrane, and this is the silver mirror as well as the search fiber. And in the next few slides, I'm going to briefly talk about some applications we do using the silver mirror as well as the search fiber. So what is a silver mirror? This is the a scheme of how to prepare the silver mirror. Actually, the preparation protocol is very simple. In this case, we have our concentrated silver nanoparticles here. We mix them with the mediating solvent, which is a organic solvent mixture. So this organic solvent or mediating solvent will adjust the surface charges of our silver nanoparticles, making them aggregate to each other. So the aggregated silver nanoparticles will gradually condense or sink into the bottom of the vial, forming a very shiny layer of silver. So we call it mirror. So you can also think of this as a film, a very thin film of aggregated silver nanoparticles. So these silver nanoparticles has many advantages. For example, it is very uniform. It creates very uniform signals. This is one of the examples we can see here on the top. On the top is the silver mirror, and on the bottom is the conventional silver colloid solutions. So let's first take a look at the picture down. So the nanoparticles we usually test them using the cold-filtering method, meaning when you mix your nanoparticle with your samples, you put them on a solid surface like gold slide or any aluminum foil slides. So this droplet will dry gradually, but one thing we cannot control is the evaporations, as you can see here in image E. So on the right side of this coffee ring, you will have a very concentrated silver nanoparticles, like the edges is very thick and dark, whereas if you see on the right-hand side, that edge is very thin and not as dark as the right-hand side. So these create a lot of variations. When testing under Raman, you definitely will detect a very high signal on the right-hand side instead of on the left-hand side. This will pose a lot of disadvantages when you want to do quantification job using these techniques. And also, if we look at image G, so this is the image under SEM, and you can see all those nanoparticles is not uniformly located. You have different layers, and you have these clusters of silver, whereas the other part doesn't have those clusters. If we look on the image on the top, image A is the wet mirror when it's not dried, so it's pretty shiny, so that we call it mirror. And then if we look at image C, this is also the SEM image of that mirror. You can see all of those silver nanoparticles being very aggregated, but they are also evenly distributed. If we look at the very right, this is the same compounds we detected. Using the silver mirror, we have a very good signal recovery, and also the signal is very uniform all across the board. Whereas if we look down, that is the coffee ring method. We only have a high signal recovery on the rings, but if it is outside of the ring or inside of the droplet, you won't have a very good signal recovery. So another advantage of this silver mirror is that it can be applied on many surfaces. So surfaces like polymers, metals, or even plant materials. So in this case, we drop the mirror on the spinach leaf to detect any pesticide residuals. As we can see here, when dropped on the mirror, on the spinach leaf, it covered the top. It covered the spinach pretty well. It still forms a very uniform mirror coating. So in this case, if we look at the right-hand side, here is the signal recovery. We can successfully detect the pesticide down to 1 ppm using the mirror method. In this case, it's the gold mirror. My bad. I was talking about silver mirror. So both gold and silver can be made into this mirror. So in this case, we use the gold mirror. So the gold mirror successfully detects the pesticide down to 1 ppm, and also the signal is very uniform. Whereas the other method, we're using the colloid solutions, you can see that signal is scattered all everywhere. And also because the nanoparticles being scattered like everywhere, we don't know where to look exactly. So that in some cases, to this low concentration, we sometimes will fail to detect any useful signals. And here is another application we use using the mirror. Another advantage we didn't mention is that the Raman techniques is very versatile. It can be combined with all the other techniques. In this case, we use TLC chips. TLC stands for thin layer chromatography. So for those you are not familiar with this technique, it is a very commonly used technique to separate different samples. Because different samples have, they bind the TLC chip differently. So if you drop it on the TLC slide, they will separate out. In this case, we tested the adulterated saffron on TLC chips. If we look at the figure on the bottom, so here we have the silver mirror stamped on the side of a adulterated ring. So what is inside this yellow area is the coursing, which is the main compounds for saffron, whereas the red ring stands for the artificial adulterants we manually spiked in the sample. So if we look at the area without the mirror, we can see that we don't detect any useful signals. All of these peaks are coming from the background. The same with the red 40 ring is that they're pretty identical. We didn't detect any useful signals. They're all coming from the background. But if we look at the area with the silver mirror, so the mirror greatly enhanced both the red 40 signal as well as the saffron signals. This mirror can also be applied to different analysis. Previously, we all talking about solution-based analyze. So in this case, we're trying to see if we can use this mirror to detect any headspace or volatile compounds. The protocol is still very similar or very simple. We drop this mirror on in this cap. This cap will be then incubated, capped on this vial and incubated with a garlic sample. So this garlic sample, like all the volatile content, will be gradually released in the air and then eventually captured by this mirror. And then we just directly measure the mirror to give us any useful information. In this case, it's the disulfide compound from garlic. As you can see that we successfully recovered its signals. All right, so that's basically the first SIRS substrate we developed. The second substrate is the SIRS fiber. As you can see here, the SIRS fiber and SIRS needle, they're basically a very similar concept. The core or the most important piece in this technique is this fiber. So this is basically a metal fiber. Then we managed to grow gold nanoparticles on top of these fiber. And this fiber is able to do any volatile detection, multi-phase detection. And in conjunction with the needle, we're able to achieve the minimum invasive analysis. I will show you in the future slides. So in this study, we're trying to determine the freshness of arugula leaves using the SIRS fiber. So sometimes it is very tricky for growers or supermarkets to know whether this leaf is expired or not okay to consume. Most of the time, these leaves will look very identical, even if it's not good to eat, or even if some indicator showing that it's not good to consume. So in this case, we put these leaves in the refrigerator in different days. Then we collect the arugula leaves, put them in a small vial together with the SIRS fiber. We incubate them for 2 hours, and then we collect signal directly from the fiber. And in this case, we use a dimethyl disulfide as the sporulate indicator. And as we can see on the top of spectra, this is the spoiled leaf spectra collected from the SIRS fiber. And this is the reference of dimethyl disulfide. And then we can see that we have 3 characteristic P that is matched pretty perfectly. So they are the CH3 bending, carbon to sulfur stretching, and sulfur to sulfur stretching bonds. So in this case, this is a review of all of the spectra we collected. The top spectra indicates the spoiled leaves, whereas the bottom spectra indicates the fresh leaves. And as we can see, as time goes on, the indicator peaks are becoming more and more significant. And moving on, by combining the collected data with Camometric method, in this case, we use principal components analysis to distinguish fresh and spoiled leaves. And as we can see here, the red dots indicates all of the fresh leaves, whereas the green one indicates the spoiled leaves. So this is a very intuitive way to show you, hey, this method is very useful to detect any or to distinguish the spoiled or fresh arugula leaves. Another example is the minimum invasive method combining SIRS fiber and a needle. In this case, the needle is working as a shell to protect the SIRS fiber. And these needle can be injected into the sample and then gradually removed from the sample, leaving the SIRS fiber inside of the sample. And as we can see here, this fiber is capable of collecting information in both, like in 3 phases. The organic phase, water phase, and gas phase all have its significant peak and they're all they can collect useful information from 3 phases. Yes. So that's briefly all of the applications we want to introduce in this seminar used with Raman. And next, I'm going to introduce X-ray fluorescence spectroscopy, which is also known as XFR. And the principle is very similar, or it's not similar, my bad. It's very simple. So when the atom or when the element atom is shot by a incoming X-ray photon, this photon will knock out some of the electrons in different shells. In this case, it's knock out the very inside shells. So when this electron leaves its original shell, it will create a void. So this void will be later filled by outer shell electrons. Since outer shell electrons has higher energy compared to the inner shells, it will emit a characteristic photon. So by detecting this photon, we'll be able to know which is the element and what is the concentration of this element. And the XRF is also a very versatile method. It is very similar to Raman. It will provide a very minimum invasive to your samples. Usually, you don't need to have a very complicated sample preparation procedure. Sometimes you can directly measure your sample in the XRF instrument. And the XRF, the detection limit for the XRF is it can be down to ppm level. However, in this case, if you're looking on the left-hand side, we successfully detect the inorganic arsenic concentration down to ppb levels. So with a better sample preparation procedure or a very good concentration method, when we can successfully detect any heavy metal or harmful elements down to ppb level. In this case, the arsenic is being generated into arsenic gas and collected by this filter. So by analyzing this filter, we can establish a very good calculations. And also on the right-hand side, similarly, titanium dioxide can be measured directly from the down-dairy creamer when it's pressed into its pellets. And also, we can use Raman spectroscopy to identify the crystal of different titaniums. Another application we made is to detect aluminum content in artificial colorants. So in this case, the aluminum concentration is in percentage level, which falls into the detection range of XRF. And as we can see here on these figures, it presents a very good linear relationship, and also the recovery is pretty good detecting aluminum. So as you know, we recently installed this XRF microscope in our course facility, and this microscope can give us more profound information based on different element channels. So in this case, we have a artificial colorants, which is yellow 5, and we manually spiked aluminum and zinc in it to mimic the artificial lakes. So this sample is scanned under the microscope, and as we can see here, we have different responses under different element channels. Here we have aluminum, iron, and magnesium. So very interestingly, we have this ring structure, and as you can see, this ring is actually coming from the metal cup that is holding the sample. And we can easily know that this is a aluminum alloy that has aluminum, iron, and magnesium in it. And also, we can see the aluminum distribution in this sample is very good. We can see it's very evenly distributed. Whereas if you look at the zinc, it's not that good distributed. We have the scatter here and there. We have some high concentration of zinc here, some low levels here. And in the meantime, we can also look for some other compounds such as sulfur and chlorine. So the yellow 5 molecules inherently have sulfur in it. So we know that the yellow 5 this sulfur is probably coming from the yellow 5 molecule, which is also evenly distributed. So this chlorine is probably coming from the processing. That is, we have some leftover chlorine in these samples. So as you know, in the previous slide, we can use XRF to do mappings. And also from Zili's presentation, we all know that the Raman can do mappings as well. So by combining these two techniques, more information or more interesting results can be made, and we call it co-localization. As a very simple example, let's bring back the TLC chips. So in this case, we developed 3 different solutions on TLC chips, and this chip will be scanned under XRF and SIRS or Raman respectively. So the first sample is just iron solutions. In this case, under the XRF microscope, we can see that the iron is traveling very slowly on the TLC chip. So in this case, we don't have EDTA here, so this SIRS this SIRS mapping is blank. And the other solution is an EDTA solution. So for those who is not familiarized with EDTA, it is a very strong chelator to bind any metals or any metallic irons in the solutions. So in this case, we successfully detect the EDTA signal using SIRS, and it is traveling very fast on TLC chips, almost to the end of the TLC. And the third sample is iron incubated with EDTA. And in this case, instead of sample 1, it's not traveling that slow. It is traveling with the EDTA solutions. So indicating the EDTA is actually binding the iron and traveling, and the iron is traveling with EDTA. So this is just a very brief examples. I know this is a very simple model, but in the future, if you have more compounds in it, you can easily see which compounds binds iron or has the best chelating capabilities for iron. So these co-localization concept can be also applied to other industries like pharmaceutical industries, where most of their products are just pills and small pellets and powders. By scanning their sample under XRF and Raman, they will be able to know their chemical distribution as well as their elemental distributions. So as a take-home message, these seminars briefly talked about our core facilities, what the instrument we have, and introduce some of the collaborations and projects we've done before. So the Raman spectroscopy, or SIRS, is a very strong technique, powerful techniques that can offer molecular fingerprints, or in other words, chemical information of your samples. So both of these techniques can do quantification jobs, but with the SIRS, we can do a very sensitive measurement down to ppb level, and these techniques are very versatile. It can be applied to different techniques. It can be combined with different techniques, and also with the development of SIRS substrate, we can expand this application capabilities. So for XRF and XRF microscope, it is also a very versatile technique to detect any elements, including element quantification and element composition. So with the help of the XRF microscope, we can even see the distribution of different elements within the samples. So during the past few years, we also developed a lot of very good collaborations between companies and as well as government agencies. So if you're interested in our core facilities or wanting to see how your samples looks under our measurements, please don't hesitate to contact our core director, Dr. Lili He, or visit our website for any reservations. Thank you, and Zili and I will be open to any questions. Okay.
Thank you, Andy. Thank you, Zili. If there are any questions, feel free to either put them in the chat or you're welcome to unmute yourself. Okay, well, excellent. If there are no questions, we'll leave it open for a minute or so. I'll thank you both, Andy. Thank you, Zili, for that great presentation and overview. I will remind folks that all presentations are online, so if you know somebody who might not have been able to make it today, who would like to learn more, they're welcome to go to the Core's website or chime in for the replay and see what the Core is all about. And I'll let you know that our next seminar will be on Tuesday, April 19th, again from 2 to 3 o'clock, and we'll be focusing on the flow cytometry core at that event. So thank you all for joining us today, and we'll talk again soon.
Thank you. Thank you, Andrew. Yeah. Bye.